minus the expected value, which is n times p, that's the binomial expectation, and then divide by the expectation again, which is n times p. That's the first thing. Okay? The second thing right here is a little bit more trickier. I'm not sure if you guys have seen this before. Sometimes in math, they do random things. And the random thing that they did right here is they add and subtract n right here in red. It doesn't change the quantity. But by doing some algebra, this becomes n minus x over here, which is the number of failures. Because if x is the successes, subtract that from the total, this is the number of failures, minus n times the complement of the success. This is the expected number of failures. So that's just O2, the expected number of failures in class 2, and the expected number in class 2. And then the denominator, n times 1 minus p, is also the expected number of failures right there. So this is the chi-square random variable or test statistic for 2 classes. Okay? Again, you don't need to know the algebra or the proof of this, but I just wanted you guys to say or to see what this guy comes from. Okay? Because this is the most basic case of just 2 classes. What happens if you have 4 classes or 8 classes? Then you're going to have 1, 2, 3, 4, 5, however many classes you have the same number of things you have to add up. So this is the most basic case. Okay? All right. So this right here, this test statistic, O minus E squared divided by E, that is the test statistic for our test today. It will be the test statistic for our 2 tests on Monday as well. Okay? So this is my attempt to just explain to you guys where this guy comes from at the beginning, so that when I go through the test, I don't have to go through that process again. Okay? Now, what happens if you have multiple classes? Not a binomial case, but you have a multinomial case. The multinomial distribution, just extending what we had for the binomial, instead of 2 classes, we have multiple classes, follows this distribution. So for those of you guys who know like multi-dimensions, this right here, these are vectors of probabilities and values. So this does require more like linear algebra knowledge, but if you don't know, then don't worry about it. But the idea here is that now I could extend not classifying my data not in just success and failures, but I could classify it in multiple classes or across multiple classes. So the multinomial distribution is just a generalization of binomial, where the class numbers is more than 2. And then for each of those classes, because I have not just success and failures, n times p, n times 1 minus p, now I might have 5 classes, and the expected value of each of those classes is just n times pi. However many classes I have, each class will have their own probability tied with it. All right, so that is something that is going to pop up today. So I'll show you what I mean by this expectation business right now. Okay, so on the left side right there, that's what we are familiar with. The binomial case where I have n objects and I need to put them in one of 2 boxes. N times, or not n times, success or failure. It goes into this box. Each observation goes into this box with probability p. It goes into this box with 1 minus p. How many observations do I expect to fall into this box? I expect n times p over here. I expect n times 1 minus p over here. Okay? So these are just expected numbers from the total. How many go in here, how many go in there. And then in the multinomial case, in this case, I have k is equal to 4. So now I have 4 boxes that these n observations have to fall into. Each of these boxes have their own probability, P1, P2, P3, P4. How many observations do I expect to fall into this box? N times P1, which is kind of similar to this formula right there. And then this one, how many do I expect to fall in this box? N times P2, N times P3, N times P4. So the reason why I'm bringing this up, I'm not even sure if any other AP Stat teacher out there mentions multinomial distribution, is because this is what we're extending what we know from binomial distribution and kind of connecting it to what we're doing with chi-squared. So again, multinomial distribution is just the binomial distribution on steroids, if you want to call it that. But this idea that we have to compute expected values for each of these classes is what we're going to need to do today. Because how do we know if what I observe from the data, because those are not data values, those are just what I expect to fall into those boxes. So what if I have data and I have a certain number that falls into here, a certain number that falls into here, here, and there, and what I want to do with chi-square is I want to compare how many observations actually fall into those boxes versus how many observations I expect to fall into those boxes. Okay, and again, it's not as simple just success and failure like we know from binomial. It is, more complicated than that sometimes. So this is the test statistic for k or more, or k greater than 2 classes. Now, if I have k classes, now I have k of these guys right here, because if you guys, well, for those of you guys who've been through calculus, you guys should know this notation. I going from 1 to k, I have k of these terms that I'm adding up, and k corresponds to the number of classes I have. Okay, so if I have 8 classes, I'm going to be adding up 8 different things. And the degrees of freedom for our chi-square for today is going to be 1 less than the number of classes I have. Okay, so if I have 8 classes, like I just mentioned a moment ago, the degrees of freedom will be 7. Okay, now, this is the test statistic that we're going to be working with. Notice how it's structured. In the numerator, I have observed counts minus expected counts. The observed counts are just what we get from the data. So observed counts is the data, how many observations actually fell into these classes. And then the expected counts are just what we had in the previous slide with the boxes. How many do I expect to fall here, here, there, there? So the idea here is that if I have observed counts, this comes from the data. So right here. This comes from the data. And then the expected counts, well, if I'm doing a hypothesis test, the expected counts, how many observations I expect to fall into those classes, is going to be defined by the null hypothesis. So this test statistic that's quantifying the difference between what I observe and what I expect is similar to what we've been working with the standardization formula from before, where we are trying to find departures from the null hypothesis. Does the data depart significantly from the null hypothesis? We should be able to work with that in this case. So the relationship, or not the relationship, but the way to think about this is that whenever we have a big difference between observed and expected, okay, this difference will be large. So if the data doesn't agree with the null, this difference should be very big. So if I continue to have data, observed counts, that do not follow the expected counts under the null hypothesis, this difference that I'm contributing to this sum is going to contribute to a larger chi-square value. So for instance, if I have, I don't know, if I have the expected counts of 4, let's say I observe, in one case, I observe 6. Then if I take 6 minus 4, observed minus expected, and I square it, then this is only going to be 4. Oh, that's not a huge thing to add up with, right? 4 doesn't contribute that much sometimes, all right? But then notice if I have an observed count that's even further away from expected. Let's say I had 10. Then that's going to be 10 minus 4 squared, which is 36. That contributes a bigger value to my sum. So the bigger departure from the null hypothesis, my observed from my expected, then it should contribute bigger values to my chi-square value. So we should expect chi-square values that are very big to be an indication of large departures from the null hypothesis. Okay? So that's the way to think about this, and this still ties in with knowing what we knew about test statistics before, that yeah, sometimes the larger the test statistic is, then the further away it is from the null value, which means it pushes it into a rejection region. Okay, so it's kind of the same concept here. All right, right now, it's a good stopping point for questions, if there are questions. So, is there questions out there? Or are there questions out there that you guys been holding on to? But this is kind of the setup for what we're going to get to today, right now, and what we're getting to on Monday with the 2 other hypothesis tests that we need to cover. Okay? And again, I don't think a lot of other stat teachers can explain what the rationale behind all of this is. Okay? So, hopefully you guys are catching on a little bit, alright? I'm not completely losing you guys, but we'll see, alright? So, going to our first chi-square test. The first one is called chi-square goodness of fit, GOF for short. I don't know why I don't have it written there. Oh, anyways, it's called goodness of fit. That's what GOF stands for. And the question that we're posing is that under the null hypothesis, I'm going to say that the population has a particular distribution. Notice that the population is cut up into, in this example, 4 slices. These are my 4 classes. Okay? And under the null hypothesis, if I have 4 classes, I could assume right now that each class is equal. A quarter there, a quarter there, a quarter there, a quarter there. This could very much be like at high school